Cool. Good evening, everyone. Thank you for joining for our session today, for our ACM ARC third session today. Today, we'll be going over a mathematical theory of communication, which was written by Claude Shannon. We briefly discussed him and his work last session when we were going over the Dartmouth uh, summer research paper proposal. And yeah, he was one of the four pioneers who suggested the study, who drafted the proposal. And he is one of the pioneering people in the field of artificial intelligence and its inception. He is also the person that uh, is credited by Anthropic in naming their model Claude, which we also used today to create this slideshow that you're looking at right now. So, a mathematical theory of communication by Claude Shannon, who was working at Bell System, Bell Systems at the time, and this was published in the Bell Systems Technical Journal, the July edition in October 1948. Uh, and I think a key takeaway from this whole thing is going to be a glimpse into how information really works. There's a lot of math in this paper, but we are not going to be going over too much of that. We are going to keep it pretty simple and straightforward, pretty understandable. And today's focus is going to be on parts one and two of the paper, which are discrete systems. And the pages that we are going to be covering from the 55 page paper are pages 1 through 24. And we'll be going over the foundation of the information age. Essentially, we are trying to solve a problem today. As I said, in 1948, Claude Shannon published a paper that fundamentally changed how we think about information. Before this moment, communication theory existed. Nyquist and Hartley had done important work in the 1920s, but Shannon unified and extended all of it. The core question Shannon answered was deceptively simple. How fast can we essentially send information? But beneath that simplicity was a revolutionary mathematic. Shannon necessarily wasn't asking that how many dots and dashes can we send. Instead, he asked something which was a lot more abstract. What is the fundamental limit on transmitting information through an imperfect channel? You might be wondering how this can be relevant to us in 2025. Well, there's a short answer and there's a long answer, but if I were to put it in bullet points, it would be compression. When you stream on Netflix, or when you are on an application like Spotify that deals with a lot of information, you are essentially using Shannon's math. The error correcting codes that you look at today, like your phone, it would be useless without them. If we look at machine learning applications, then LLMs like Claude rely on information theoretic principles, any LLM. And channel capacity. Why is 5G faster than 4G? Well, that's literally what Shannon's theorem is actually about, and we'll go over that. Um, Before we do that, I want to go ahead and say what we'll cover in the next hour. Today, we'll be walking through the paper section by section, and we are looking at part one and two, the discrete case, which is the foundations. We'll avoid the continuous calculus, which is the majority of the math for part three, and we can have another session going over the math, like in that session. Essentially, if I were to encapsulate the journey, it would be something like the communication system first, as in what are we trying to model? There's measuring information, which is the birth of entropy, channel capacity. How fast can we actually send data? And noiseless channels, which will be an ideal case. You must have heard of this case where a frictionless environment or a perfect world, right? So a noiseless channel, which would be the ideal case, which yeah, so there are no noisy channels in there. Another variable we are considering are noisy channels, which is the real world. Equivocation, which is how much information usually gets lost when transmission happens. If even if you look at, like, a steam engine, a lot of the energy is, it's not used to power the train forward. Most of the energy which is burned, which is the coal, it's dissipated by the engine's mechanism, and heat is flowing outward, so it's wasted. Like the steam piston engine there is wasting that energy. Yeah, and it's dissipated. Like the movement itself is facilitated by the heat, like cooling of it, and then the piston moves and then removes, and then it comes back again and then moves again, and it does that. But in that process, like in that channel, some heat is just dissipated away. So we were bottled at 33% maximum efficiency of an engine, no matter what, because of these constraints at one point. But then more innovation happened, locking it, and making that environment like stable happened, and then we rose to like 67%. But 33 was like a theoretical max at one point because of this simple thing, and it translates here too, right? Like equivocation, how much information is getting lost when I'm sending a packet of information to you, how much of it is actually reaching you, and what is getting lost in the noisy, like channel. Then there's the fundamental theorem, which was Shannon's main result. And there's also modern implications that we'll be going over, that why is it still relevant, and why does it still matter? Now, let's move. Okay, so the historical concept. Pre-1948, Nyquist in 1924 and Hartley in 1928 were the pioneers who laid the groundwork. Existing technology at that time was telegraph, telephone, radio, which were practical, but they didn't have any unified theory to them. New challenges proposed themselves. Modulation schemes like PCM, PPM, they needed a framework, which were, which was not present at the time, because no unified theory essentially existed. Shannon's contribution to this was a unifying theory that was spread across all communication systems, information theory, rigorous treatment of the noise effects, and an analysis of statistical structure in messages. You can reference this specific, like thing, and I'll be doing this like going forward for all sessions too. When I am discussing a concept, I'll tell you which page of the reading that I shared prior to the event you can find it on. So this historical context can be found on page number 1, introduction of the paper. Moving forward, the fundamental problem, reproducing at one point a message selected at another point. When a message is sent out from one starting point, how do you reproduce, like you transmit, it's received, and then how do you reproduce it as it was, minimizing as much loss as possible, and then reproducing it so that you can look at it or understand it at another point. I mean, it's not necessarily exact. It can be an approximate. Like it doesn't have to, it won't be like, the real thing. Like that's what people say with like, teleportation of human beings too, right? Like if you like were to move from this point to another point, and we'll get into this later, you can't be the same, like, thing. It'll be a deconstruction of, your atoms, and then you leave a void here, and then at another point more atoms will be put together again to create you again. It'll be the same structure, it'll be the same, like it'll be the same looking thing, and it'll be the same kind of things interacting with each other, but it won't be the same particles. Like it'll be a reproduction. Teleportation, yes. And there will be loss, like maybe you will lose an arm is a far-fetched thing, because if you look at best practices, I would like it in a way that, okay, the bone structure is done and then muscles are put on top. I would say that, think of it like a cheese, right? Like a cheese slice of cheese. Like it'll be a cheese slice, but it might have a hole here and there, like, you know what I mean? Like it'll lose like some fineness, and it'll have like some small dots here and there, and these would be the inaccuracies. Critical insight from this is that meaning is irrelevant to engineering. Semantic aspects of communication are essentially irrelevant. Like the semantics of the conversation, they are irrelevant. The significant aspect is message is one selected from a set of possible messages, and communication is equivalent to selection plus transmission plus reconstruction, like I just said. Okay. Well, let me start with like, a diagram that Shannon draws upon on page one. I don't know if it's sure or not. Yeah, there is a paper. There is a diagram and it's on page two, not page one. Sorry about that. If you look at this diagram, then essentially there's five essential components to this diagram over here, which would be the information source, which produces the message that has to be transmitted. There is the transmitter, which encodes this message into a signal of a sort, which will be the thing that itself is transmitted. The channel, which is the medium through which the message will be transmitted. The wire, the radio wave, the fiber optic. There's going to be a receiver, which reconstructs the message from the signal. There's going to be obviously a destination where this receiver is placed, and the person or the system receiving the information, this is the destination. And then there's going to be noise source, which is the adversary. So there's going to be noise in the medium, so the channel will have noise and there will be a noise source. Why this model, right? Like, we might wonder why this model. Shannon makes a critical philosophical move between pages 1 and 2 in his paper. Goes on to say that the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. The fundamental problem of communication is that of reproducing at one point, either exactly or approximately a message selected at another point. So that is literally his, like, issue. That is the dilemma. How do I reconstruct something at another point, a message that was sent out from another point, right? Like the teleportation problem here. Will it be real? Will it be the same thing? Frequently, the message has meaning. These semantic aspects of communication are irrelevant to the engineering problem, is what Shannon says. Notice that it doesn't matter what the message means. What you care about is what the structure of the message is. You don't care like what it essentially means. You don't care what the semantics are. Like, I am a boy who likes eating chocolate as a sentence. I, boy, eat chocolate. I, boy, like eat chocolate. That's the same thing, right? The semantics are missing here, but the message is conveyed. Now, look at this, right? Like, frequently the messages have meaning, but these semantic aspects of communication are irrelevant to the engineering problem. This is revolutionary because Shannon strips away all context, all emotion, and all meaning. He says that from the engineer's perspective, communication is about transmitting one message.
Before Morse code was a thing.
No, this is way after Morse code was a thing.
So, okay. No, what I'm trying to say is that, like, there is a way to do this, but like through, very abstract sources of communication.
Yeah, what if your mom wanted to call you and say, I love you? She's not going to be like, like, that's not fair, right? Okay. This is revolutionary, right? Because Shannon strips away all context, emotion and like semantics and like meaning. And he says that, like, from the engineer's perspective, communication is about just transmitting, like, one message from one set of possible messages. Um, a practical example of this is telegraphy. So the source is an operator, the message is a sequence of letters, signal is dots, dashes, and spaces. Think of the radio. Source is a microphone, message is the sound wave, and signal is modulated electromagnetic wave, right? Your brain to a friend. The source is your thoughts. The signal is acoustic waves, which will come out of your mouth, and the channel is air through which it's transmitting. Receiver is going to be your ear and your eardrum, your canal, whatever. Also your brain, which will probably process and make sense of it, right? So Look, he's trying to translate real world things that exist at that time and trying to unify them towards one conformed information theory. Like, basic concepts in this architecture on page number 2, which are information source and the transmitter, which make up the message. There's a signal sent out and to the receiver, which is next to the destination, and that is also reproducing the message. And between this channel is the channel of communication, and there's a noise source that produces noise. So fundamental, right?
Yeah.
So fundamental that you take it for granted.
Exactly.
Right? And then you see that, wow, this can actually be used to, like, convey any sort of information transmission or information exchange, right? It just unifies it together.
Yeah.
Revolutionary. A key question that you want to ask here is, what if I told you that the meaning of the message doesn't matter for determining how fast we can send it?
Meaning, wait, what do you say? What?
What if I told you
Yeah.
that the meaning of the message doesn't matter for determining how fast we can send it?
That's usually by meaning, you mean like length, like the amount of bits, or like just like, because that would be normal, right? That would what you would be. That's what you would expect, right? The whatever is the content of the messages should not matter.
So length is a different variable because that will tie into the answer, which is efficiency. But what I'm saying is that, remember that guy from the office who said that why use more word when less do job? Yeah. So it's like the message itself, like I was saying, like I'm a boy who likes eating chocolate, or me boy like eat chocolate, right?
Yes.
So it's like, what if I told you that the meaning of the message, like the
Okay,
actual
so the
meaning,
meaning stays same, but
yeah,
like the structure is changing.
exactly, like the meaning doesn't matter for determining how fast we can send it, right? Like why that might be. Well, the reason for that is that the channel doesn't understand the meaning.
Exactly.
Right?
Yeah.
The channel is agnostic, like it doesn't care.
doesn't.
Like for all I know, like it's just particles that are trying to do their own thing, and it's me who's speaking that's disturbing the equilibrium of these particles, right? I'm the villain here,
Exactly.
actually. So it really doesn't care like what's happening. It only transmits signals, right? A channel doesn't know English from gibberish, and they are both just symbols to move. Now, the only thing is like speed of sending it is literally a factor of how can you condense it, how can you like make sure that it goes faster, as in a pipeline. Like, do you cool the air and it makes the sound go faster?
Yes.
Because you know that
Yeah.
like when air is colder, things are more coherent.
Yeah.
It's traveling faster together. And like in the winter time, if I were to stand here and you were there and there's mist in the middle, scream TV, you hear it quicker than right now when it's clear and crisp and all that.
Is that true?
That is true.
Okay.
Try it out then. We can try it out when winter rolls around. Maybe after one of our ARC sessions. But yeah, so yeah, that is the reason, right? The channel doesn't understand meaning; it only transmits signals. A channel doesn't know English from gibberish, right? Both are just symbols to move. Um, well, let's see. Messages and signals both are sequences of symbols. The telegraph will use, as I said, dots, dashes, and spaces, and a teletype is using 32 symbols. These are discrete types of communication systems. There are also continuous types of communication systems, which are built on the fact that messages and signals are both continuous functions. In discrete, signals and messages are sequence of symbols, like in the telegraph, dots, dashes, spaces. In continuous systems, messages and signals both are continuous functions, like the radio or telephony, right? Like I call you and then it's a signal that's going. Then there's also mixed communication systems, like which will contain both discrete and continuous variables, like a PCM transmission of speech.
So what exactly is, yeah.
So I say, and then it's transmitted like dot 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 dot. So that,
It's like a translate.
yeah, so essentially it's like it's essentially mixing the two, like frameworks together, because you okay, you don't want like someone to understand what your nuclear codes are, I guess. So you encrypt them in a way and then you transmit them,
Okay,
right?
yeah,
So
that makes
that
sense.
could be considered a PCM. Okay, let's get into like a little mathematics here. Um, Although I said that there won't be too much math, but there is a little math. So let's like do a setup here, which is Shannon is trying to formalize this idea where the information source produces a sequence of symbols chosen from a set.
Mhm.
In telegraphy, for example, it'll be ABC through Z and space. The transmitter transforms these into channel signals. The receiver does the inverse. So the transmitter that we have on our end, it'll take these symbols and then make them into channel signals. The signals that are understandable and transmittable by the channel. The receiver is the inverser. So it'll let the channel communicate to it. It'll take it and it'll inverse it, back into the symbols from the transmissions. If we look at like a description, it would be information source, message sequence. There is a transmitter right here. It encodes the message into the signal that has to be sent out. There is a medium here where, the channel through which it will be going with noise. It will get some noise from somewhere. And then there will be a receiver over here that will receive the message.
Yeah.
It processes it and converts it back into the message. And my friend over here who's looking at it, they are able to get it. That's the destination. So that's like painting a picture of what we are looking at. Everything good until now? We all get it?
Yeah.
Okay, cool. Now we'll ask one question here, which is, why are we, and this measurement happens on a logarithmic scale. Do you guys have any idea about what logarithmic scales are, or what logarithms are? Or okay, so essentially think exponential, right? So wait, so think linear, and then think like exponential.
Yeah. So linear turns to exponential, or like?
No. So linear is this, like it's, dependent
Yeah,
code,
yeah.
whatever. Exponential is like every value, and then, yeah, and then logarithm is even, it's even steeper than that,
Okay.
essentially. What logarithm is like, okay. I think if I had Mo here, he could explain this like much better, because he's good with the mathy aspects of these things. But logarithms are like much, much more compounding than the scale of exponentials or linears. And what it means is that it's trying to define things like in respect of powers. So like log anything of.
You're just trying to explain logarithms now, but yeah.
Okay. Cool. Anyways, I'll just say why he uses a logarithmic measure, and you'll get to the math at some point yourself. Anyways, three reasons that Shannon gives for using this math that he actually does are practicality, the engineering parameters like time, bandwidth, and relays scale linearly with log. So that's one reason he gives, that if you add like one relay and you double the states, then it increases the calculation by only one. Like it doesn't, like in a linear, for like one you get one, for two you get two. That is linear like growth. Okay. Exponential may, for one you get two, say for two you get four, for three you get eight, right? If you add, like if you double states, so like say you keep log 2 like as your measure, right? Then it scales linearly, so that like for every doubling of states, there is one growth. Does that make sense? Like every time you double the state. So
For
like,
example, you're starting from like log 2, then becomes log 3, or
no. So say like it's we start with two states.
Okay.
And then it's at one. Okay.
Yes.
If we have four states, then it becomes two.
Two.
If we have eight states, then it becomes three. So here it's a different function. It's not like for one you have two, for two you have four, for it's like for two you have one, for four you have two, for eight you have three. So every time you double these states, and it's going to increase by a value of one. So are you able to like understand that at this point, every time we want to increase the y here, we have to literally double the states. So the number of the number of like calculations that you can do for every increase are like a lot. So say like 500 people are like in a lottery.
Yes.
The chances of you winning out of that is 1 of 500, right? It's better explained in terms of log, that probability that order of computation to comprehend it, it's better explained linearly in log than it's explained in linearity, is what the whole point of this thing is, because it deals with an order of computation that we can't comprehend. And to make it comprehensible, we use log because it scales linearly compared to the log, if that is a better explanation. Okay, say we double the time and square the number of messages, then it becomes double. So like you have to, like you have to double it to get like a linear growth, and then you have to square it to get like a exponential growth. So you already see that the power that this form of calculation holds is much immense compared to just a linear or quadratic, because these are a function of this here, right? So it's exponential scale that we are talking about. Anyways, it's very intuitive. So say that two channels have double capacity, then two coins will have 2x storage, not 4x storage. Anyways, let's move on from that. Mathematical sincerity of this concept is that limits and operations are cleaner in log scale calculations. I'll say that it's just more feasible to do it this way, is why we are doing it. A little rundown of some basics. I know you know what a bit is. Bit is a binary concept. It's 0 or 1 usually. Log base 2 means resulting units are bits. So what we are doing is we are giving a binary here that everything will either be a 0 or a 1. And this was named by J.W. Tukey, and this is also mentioned on page 1. Physical interpretation of this is one relay. Matlab, if there's like one wire that's going, it can have two states, on or off. So that is a bit, like on or off, 1 or 0. Okay. That's what one wire is supposed to represent. N relays means n bits, and then the number of combinations becomes 2 to the power n. So every wire has one possible, every wire has two possible states. So if I give you n wires, so think of it this way: if I give you three wires, how many possible states can there be total combinations? Eight, right? What is that? 2 to the power 3. So there's a relation here, 2 to the power n. So if you have n wires, then the total number of possible states are going to be 2 to the power n, right? Very intuitive. Cool. Okay. N relays matlab n bits, since 2 to the power n states is log 2, 2 to the power n equals n. So see, log math here helps us understand it a lot better and intuitively. मतलब कि 2 to the power n, if taken to the base of log 2, is will give you n, essentially, is what it's saying. Because the n carries over, it becomes n log 2 base 2. Log 2 base 2 matlab log x base x always gives a 1. You're left with 2. Anyways, alternatives to this is log base 10 is decimal digits, and log base e is, yeah, natural log. Also, something to keep in mind that I'll say right now is uh, start thinking of uh, start thinking of units in like in a time signature type of way, like you do in music, like 4 by 4, right? Like 1 2 3 4, 1 2 3 4.
We're not considering it in decimal.
Yeah. Yeah, I mean, so for to understand that concept, like think of everything like an information, like bundle, like time. Your hour hands are 12, right? So you're counting in a 12 base system there. So every 12 is like what? Half a day, right? So what is that? Every 24 is one day. So you're counting in a 24 or a 12 base system. They say, right, like 12-hour time, 24-hour time. What is that? It's a way of, like, it's a way of counting. So think of number systems like that now. Like every 10 is one something, right? Like every 10 is a, let's say, decade. So you're counting in a 10 system there. So you are fundamentally here challenging the way you count. What is a binary? It's a two counting system. 1, 2, 1, 2. Every 2 makes 1. So 0, 1. And then when there's a 0, 1, and then when you have to do 2, what is that? So 0, 0, 0, 1, and then 1, 0. 1, 0 is 2. 1, 1 is 3. 1, 0, 0 is 4, right? So you're in a two base counting system there, where every 2 gives you one, like, more, right? So start thinking of things like that. What are octals? Octals are 8 base counting system? What are hexes? 16 base counting systems, right? Think of things like that now. So, you'll get more clarity. Okay. So, you know that natural log is log base E. Okay. Let's think about the birth of this mathematical concept now. This is where Shannon makes his key intellectual contribution, and he says that he needs a mathematical definition of information, not the dictionary definition, but a mathematical measure is what I was talking about right now. The problem is how much information is present in a message, right? Like how, like, say, okay, bet, like you don't care about what the message is, but we do want to know like how much information we are sending, right? Because that is something that we want
Yes.
to worry about. That is
Yes.
something we can quantify. That is something we can optimize. That is something we can crush down a little more to make it a little more efficient to send. Comes later, but that's something we have to do, right? So think of it. How much information is stored in a message? On page 2 of the reading, Shannon starts with the question: if we have n equally likely messages, how much information or choice is actually involved? He argues for a logarithmic measure, and here's why. There's a practical utility, like I was saying. Engineering parameters scale linearly with log, which is the amount of possibilities that can happen.
Mhm.
You add one relay, you double the states, which is like, adding one bit to it. Every relay that you add will double the states essentially, right? Multiplier by 2. Permutations and combinations, right?
Yes.
So every time one more is added, why is it 2 to the power n? Because every time another n is added, multiplied by n, 2 to the power n times n is 2 to the power n plus 1. So what is it doing? It's actually doubling the state, right? It's literally, so every time you add a relay, you're doubling the number of possible combinations here. You see how that can scale linearly with the log now? How difficult would it be to, like, explain like in a quadra, right? Or in a, sure, you can plot it, but can you make any sense of it? No. But if you scale it linearly like that, you can actually see what is happening, right? Like doubling states happening here, and this linearly increasing by a value of 1. Very highly intuitive, right? Okay. Even I understood it right now, and I was like, oh, mind blown, right? Double the time, right? You double the time, and what will it do? It'll square the number of messages, which is doubling the log itself. It's highly intuitive. Like I said, two identical coins have twice the capacity of one coin, right? Like one coin is 2, two coins is 4, three coins is 8, four coins is 16, right? Mathematical limits and operations, like I said, are simpler explained with logarithms. The unit is 1 bit. We use log base 2. We get bits, a term coined by J.W. Tukey. One relay is one stable state per bit, and it can store 1 bit. One relay can store 1 bit, which is one on or off switch. N relays means 2 to the power n states. Log 2 to the power n by the base of 2, log of base 2 gives n bits. We went over all of this. 1 bit is the information in choosing between two equally likely outcomes, a binary, right? Now we come to entropy, which is the master formula here.
Yes.
Now comes the actual genius of, Shannon's information theory, um, where on pages 10 and 11 he goes over defining what entropy for a discrete probability distribution actually looks like. If we have n events with the possibilities p1 and p2 um, times pn, then the entropy can be represented as you should look at the like literature right now to look at this exact formula. It's on pages 10 through 11 if you want to go over here. Um, sure. If you want to go over that here, it's on pages 10 through 11. You'll see a formula, which is essentially a summation from I equals n to n, and it'll be pi by log pi with the base of 2. Why do we do an inverse here? It's because the higher the number, the lower the probability is going to be. Think of it like winning the lottery essentially.
Which page is that?
10 through 11. Do you see a formula over there?
There's like a
Here?
bunch of them.
Here, this one.
Yeah, yeah. No.
Yeah. Essentially, H is what is defining the entropy over here. Think of it like winning the lottery, right? Like a billion people like are fighting in this lottery to, win it, and say your chances of winning are 1/1 billion, right?
Yes.
It's a very small number which can be represented very clearly using, a logarithmic scale here. And how surprised would you be if you didn't win the lottery? Not too much, because
Yeah.
the odds are just too skewed. But
Yes.
if you did end up winning, how much excitement do you think you can have? Because it's a 1 in a billion. Like, a 1 in a billion thing will excite us a lot more than 1 in a 2 thing.
Yes.
And that is the reason we look at this equation like this. The negative sign actually makes it positive, because we use log base 2 for bits. Um, there's a theorem here which says that Shannon proves that this is the only function satisfying three reasonable properties. It's continuous in the probabilities. For equally likely events, it increases with the number of events, and it's additive for sequential choices. So when there's sequential choices to be made, then it like adds the probabilities together. For equally likely events, it increases with the number of events that take place, and it's continuous in the probability. So it can be represented continually in terms of probabilities. An intuitive understanding of this can be understood and could be understood using a fair coin flip. Um, in a fair coin flip, it's usually a heads or a tails. That's what I know from all the coins that I've seen. Unless you have a coin that has two tails, or two heads. Each probability is going to be a binary, which is a 0.5. Say you plug it into this formula, then h equals minus, probability of 1 over log 2 of 0.5, which is the other, plus 0.5 divided by log 2 of the other, which is 0.5 times 1 plus 0.5 times 1, and it ends up giving you 1.
Be better if you like wrote this down somewhere.
I did write this down somewhere. I also have it on the slides here, so you can look at it from there. It's on slide number 8 of 25. The Claude artifact that I shared.
Yeah.
The entropy fundamental formula, which is
Yeah.
H equals negative summation of
Yes.
I times pi log 2 pi. Uh, don't worry about it too much. Just think of it like pi is the so summation. What it's going to do is it's going to add everything.
Yes.
Okay. And it's going to do it I times.
Yes.
That until that you're clear, right?
Yes.
Okay. Now what is pi times log 2 pi? It is the probability of this thing happening times log 2 of that thing happening.
Okay.
And then you multiply these two together, and that is for I. So I equals say 0.
Yes.
And I equals, and your conditions are from I equals 0 to n. So what it'll do is multiply these two things together for I equals 0, which is pi times log pi.
No.
It multiplies them here. Then 1 multiplies 1,
Yes.
then for 2, then for 3, then for 4, all the way until n. All of these multiplications have been computed now.
Yes.
And then you add them all together.
Yes.
What does it give you? It gives you entropy.
Yes.
That's what this formula is. Does that make it a little clear?
Yes. If
Okay.
you could go over the definition of entropy again.
Okay. So entropy is not defined here, but we will get to it, like,
Okay.
in just a little bit.
Yeah.
Think of entropy as like, and entropy is literally my favorite word in the whole world. It's because I believe that everything that's happening is an agent of entropy.
Yeah.
Entropy is, well, slow destruction or fast destruction. Well, destruction. That's what entropy is. Entropy means in this isolated system right now, like if we were, say, locked in this room forever,
Yes.
what's going to happen? Everything is going to decompress. First, I'll get very hungry,
Yes.
and then I will not have food anymore.
Yes.
So I'll either have to, like, get rid of one of you, and then, I'll have food for a while, but then
Yeah.
I won't have that either.
Yeah.
You see how things slowly start deconstructing, and then
Yes.
until nothing is left in this room, essentially. The energy will stay constant, but things will get destructed.
Yes.
That's what entropy is.
Yeah.
Right?
Yeah.
So that's what, and that is why now try to think, like, it's not apparent yet, but do you think this is suddenly tying a little to information theory here, like deconstructing something, sending it, reconstructing it, energy staying constant in the system?
Not really.
Not really. Okay,
Yeah.
let's see how it becomes intuitive
Okay.
going forward.
Yeah.
Okay, so three axiom that satisfies this formula are continuous and probabilities. Monotonic, so for equal probabilities, it increases with n, right? Naturally, don't you think it will increase because it's so like I have n, right? And I multiply everything until that point and I add them. What if it became n plus 1, right? You are literally just adding one more to it. So obviously it's going to increase as the number of n increases, right? Is that like intuitive?
Yeah.
Okay. And then it's additive for sequential choices. I don't know what that means, but let's just say that it's additive for sequential choices. Okay. Key insight. This is the only formula which they ran and found which would satisfy all three of these axioms. And the terminology is the entropy of the set of probabilities. That's what the that's what the name has been given to H, which is entropy of the set of probabilities. Let's just leave it at that. Okay, no more math for this. Um, One last thing, I'll explain the fair coin thing again, which is fair coin will have two probabilities that are possible, 0.5 of getting heads, 0.5 of getting tails. The number of bits are one. It's a binary choice. If it's a biased coin, say with the probability of getting head 0.9 and tail getting 0.1, the number of bits becomes 0.47 if you plug it in the formula.
And what's the significance of that?
The significance of that is that is the entropy and the heatness of the system. Like the probability of you accurately determining something is going to be
When
0.47.
it was 50-50, what was it?
1.
And because you changed it to 9-1, it became
0.47.
okay.
Yeah. And then say it's a certain coin that it always gives you either 1 or 0, right? Like you just know that it gives you head. Then the number of bits is 0 because you just, know what the answer is. There's three equal events that can happen. So say like, 1 by 3, 1 by 3, and 1 by 3. This is not from the coin example right now because a coin doesn't have three sides. Then the H, which is the number of bits, it becomes 1.58. Like if you plug it into the formula, multiply by, so like log base to 1 by 3 multiplied by 1 by 3. We'll just do it three times because all of them are 1 by 3. You'll get the heatness of 1.58. That's what the H, the number of bits in the system are. Okay, cool. H means uncertainty. Entropy, to answer your question, is uncertainty. Okay. More certain means low entropy. So see a certain coin which has the condition of 1 and 0, like it will always give a head and never a tail. The entropy there is 0 because it's so certain.
There is no uncertainty.
No entropy, right? No uncertainty. Max entropy occurs at equal probabilities. So you will see that the 1 by 3, 1 by 3, 1 by 3 example, it gave the most heatness, which was 1.58. Intuitive, right?
Yeah.
We are all with me so far. Okay, great. Awesome. So there is 6 properties of entropy that are described in this paper. Okay, we'll go over them like, slowly and steadily. H equals 0 if and only if all probability is certain on one outcome, which is a certain outcome. So the uncertainty of something happening is determined to be 0 when all of the probability skewed towards one event happening. We just went over this, so it's pretty. H is maximized, so uncertainty is maximized when all outcomes are equally likely. So uncertain, right? Like, who knows what's going to happen? Because all of these outcomes are equally certain to happen, right? H max will be directly equivalent to log n. Okay, just remember that. Joint entropy is equality if they are independent. So h of x and y is smaller than equal to h of x plus h of y. Let's just leave it at that. Averaging increases h. So making probabilities more equal raises entropy, which ties into h is maximized when all events are equally likely. So if you increase the averages, so if you normalize more and more, the entropy will naturally start to increase in the system. Conditional entropy is uh, h of h of x when y will be equal to, like, their joint entropy minus h of x. Don't think about this too much. And there's knowledge reducing uncertainty. So when knowledge is introduced to the system, which is literally removing uncertainty, think of it from a philosophical perspective, then uncertainty will also be decreases, and naturally entropy will also decrease because context is being added to the system. Okay, deep connection here. The same formula as entropy can also be found in thermodynamics. So math stays
Yeah,
constant,
yeah, yeah.
physics stays constant, is what it's trying to
Yeah,
say.
because originally I thought entropy was a physics concept.
Yeah, it is a physics
Yeah.
concept, but here it's also applicable here. So we went over, the six common properties, which are six beautiful properties, which is H equals to zero, entropy is zero only when all probability is on one outcome. Otherwise, H is greater than zero all the time. It'll never be less than zero. For it's a okay. For n outcomes, H is maximum and all are equally likely to happen. Just went over this. And in this case, H equals to log n. H max is always equal to log n. Okay. Joint entropy satisfies, the condition that we went over with equality only if they are independently happening events. Okay. Then a joint entropy happens. Let's just leave it at that. Any averaging operation, which is normalization, will make probabilities more equal. And what will it do? It increases entropy, right? Good, good. Maximizing will be when all events are equally likely to happen. And there's conditional entropy, which is h of we went over that. And property 6 is that knowing x cannot increase uncertainty about y. Okay. A striking analogy. Shannon notes on page 11 of the paper that this is the same formula as entropy in statistical mechanics. In thermodynamics, it measures disorder. That was the definition that I was defining, disorder in things, right? Okay. Now let's come to the practical meaning of this. That was a lot of math. I mean, it wasn't too much math, but like still, it can take a toll on us. But coming to, and I can already see Saha clocking out, but he has hope and he's sticking to it, which I'm very happy about. Okay. So let's come to the practical meaning of this thing. Like, why did I make you go through all of this? So on page 14, Shannon calculates the entropy of English text. Okay. Interesting. The redundancy of English is roughly 50%. So there's so 50% of it is just redundancy, inefficiency.
Yes.
Okay. Meaning, what is the meaning of this thing? Is that half of what we write is determined by language structure. Half is just free choice. This is why crossword puzzles work. Let's think of it. Entropy in bits. A fair coin has, 1.0. Biased coin has 0.5. And a certain outcome has zero point 0 with probability being p. Okay, let me go here. Oh, before that, I do want to talk about one more thing, which is channel capacity. Um, Man, this is more math, and I really don't want to overwhelm you. So I'm not going to go over too much, but there's just a formula which says that channel capacity, the capacity of the channel, as in like the amount of information that can flow through this channel. Okay, there's just a formula. I'm just going to say it. Just keep it in your mind and never think about it again. Okay, is C equals to limit where t tends to infinity log n of t. So n is a function and t is the variable you put into the function divided by t. Okay. So the t is tending to infinity, meaning that the bottom t that we have, it's tending to infinity, which means that it's becoming smaller. The whole thing is going to try to become smaller. Log n of t is already a very small thing, and that is the channel capacity. The interpretation of this formula, oh, where nt is the number of allowed signals of duration t, number of allowed signals of duration t. Okay, nt is number of allowed signals of duration t. Okay,
By allowed signals, you mean like
allowed signals, right? Like number of,
oh, okay, okay,
yeah,
okay.
number of firings that you're doing
Okay.
essentially.
Yeah.
And log of that divided by t, where t tends to infinity. That's also not that
So what
difficult.
is T1 and so T1, T2 would be like the signal itself? Okay.
Yeah, signal containing information.
Okay.
uh Sorry, t is the uh duration of the signal. Like,
Oh, okay, okay.
okay, so interpretation of this formula, which is counting valid messages fitting in time t.
Mhm.
Take log, divide by t, take limit. The units are bits per second if using log of base 2.
Mhm.
Example of this, so it's a little clear.
Yeah.
A teletype does 32 symbols in any sequence. C, according to this formula, is log 32, which is 5 bits per second. What is log 32? 2 to the power 5 is 32. So it does 5 bits per second.
Yes.
That's what this formula calculates. It counts the valid number of messages fitting in time t. Right? This is intuitive. This is intuitive. Trust. Telegraph. It is a little constrained where C is 0.539 bits per symbol. Okay, let's move on. State-based channels and theorem 1 by Claude. Generalization here.
Okay.
Uh, pages 3 to 4 in figure number 2. Yeah.
Yes.
Yeah. So the theorem is C equals log W. If M possible states exist, A1, A2, all through AM, from state I, like any state I, only certain symbols can be transmitted because we are breaking them down. Each symbol leads to a new state. Do you remember what states are?
Yeah.
Okay. Telegraph's example. In space, question mark, determine what's next. So I am in space and in the empty space, and I have to decide that what is coming next now. So the theorem is C equals log W, where W is the largest real eigenvalue of the transmission matrix. Graph representation of this would be that nodes are representing states and edges are representing transmissions. This is too high level for you, don't think too much about it. Markov sources and stochastic processes. So there, I'll just give you some examples of what this term means. Don't think too much about it. There's a Markov property which says that next state depends only on the current state. Remember that, okay? The next state depends on current state. You remember this, Shubhadeep, from the first paper, if I'm guessing it right. If you know current state and all the calculations in it, you can determine what the next state is going to be. That is Markov's property, okay? Representation of this will be using a graph where the nodes will represent the states and labeled edges will represent the symbols with probabilities. Okay. Examples in paper that talk about Markov sources and stochastic processes are independent symbols, which are singular states, diagram models, which are two-letter dependencies. There's a trigram model that is three-letter dependencies. Remember, I told you to count in twos and eights and 16s. That's what this is. A word model where structure words have probabilities. That's what LLMs do. They have words with probabilities about which word should come next, which state should come next. Okay. Let's move forward. Yes, all math has gone now. Okay, so the English, right? Like 50% of it is just redundant. The oth order, sorry, the zeroth order will say that all letters are equal, which is uh, a random set of gibberish letters. The first order will say that English frequencies, where some letters are more frequent than others. Second letter or second degree order would be diagrams, where things are in pairs and they make some sense.
Yes.
Third order is trigrams, where they may make a little more sense. First order words, representing and speedily is, and so set of words that actually make sense. And second order words will be an actual sentence, like the head and in front attack on an English writer, whatever. Key insight you can take from this is that structure gives recognizable output, which means less entropy. More entropy means more disorder, which means the zeroth order will have the maximum amount of entropy and the second order word will have the least amount of entropy.
Second order being full sentences.
Yeah. Math can replicate language. Okay. Moving on to the
Crazy to think about.
yeah. Moving forward, ergodic and mixed sources. What is an ergodic source? All sequences have same statistical properties, which is statistical homogeneity. Any long sequence is representative of the entire source. Bless you. Bless you. Requirements for an erodic graph. Connected. Can reach any state from any state.
Yeah.
And aperiodic is going to be, the cycle length is going to be 1. Mixed sources will have a blend of erodic components, and it can start in one component and stay in it forever. Why does this matter? Because it allows ensemble averages or time averages, which are more complicated ways of looking at this. Oh no, there's more math after that. Okay, let's come to another section, which we just went over, but we'll talk a little about it.
Yeah.
Discrete noiseless channels, the best case scenario, and channel capacity. So from page 3, a discrete channel transmits symbols from a finite set. An example of this, as I went over, was discrete. Remember? Telegraphy, which uses dots, which uses dashes, which uses spaces. Teletype, which uses 32 symbols exactly, 0.5 something. Digital communication, which uses 0 or 1, like a binary. Each symbol has a duration and the channel has constraints. Not all sequences are allowed, right? You can't expect to put 0 and 1 in a teletype. You can't expect to put 32 symbols in a telegraphy because it has its own way of communicating, right? Defining what a channel capacity is. So, giving you a better example. The capacity C of a discrete channel, like I gave in the formula, is C limit t tends to infinity, a fraction where we use take log nt divided by t, where nt is the number of allowed signals of duration t. In English, count how many valid messages fit in time t, take the log, divide by t, and then take the limit, tends to infinity. Example 1, a simple teletype. 32 symbols, each 1 unit of time, all sequences allowed. In time t, we can send t symbols, right? Because each is 1, okay? Number of sequences is 32 to the power t. So the capacity becomes a fraction of log 32 to the power t divided by t, which will, come down to approximately 5 bits per second because, 2 to the power 5 is 32. Constraint telegraphy, where 1 unit of closure is plus, where dot is 1 unit closure plus 1 unit open. A dash is 3 units closure plus 1 unit open. A letter space is 3 units open. Word space is 6 units open. And constraint is no consecutive spaces. If calculate based on the formula here, you'll get 0.539, okay, as the C, which is the constraint of the system here. And then there's state-based channels, where Shannon formalizes channels with memory or state constraints using finite state machines, which we went over earlier. Imagine m possible states. From each state, only certain symbols can be transmitted. Each symbol leads to a new state. Probability transition matrix can be encoded as a graph. So for this, there is one theorem which I'll go over, which is for such channels, C is log of W, where W is the largest real eigenvalue of a matrix derived from the graph. Whew, okay. Intuition. Why is this thing state-based? The telegraph example. Let's take the telegraph example. Are we allowed to send another space is my question. Okay. Can I send another space is the question I'm asking in the telegraph, scenario here. If the last symbol was a space, then no, we are in a space state right now. So no, it's not allowed to send right now. If the last symbol was a dash, then yes, we are in a dash state. Do you see how state just defined what our next state is going to be? Was that clear? Yeah. Right? So essentially, we are using a state-based mechanism because here, one state, the previous state or the current state, is determining what the next state is going to be. That's literally what a finite automaton is, right? So it's completely dependent on the state that you're currently in. And this is what the channel remembers. It remembers what was sent and restricts the next symbol. That's the memory. Remember the Turing tape that we went over? That's what this is. Diagram description of a telegraph state transition. There's a dash or a dot, there's a letter state. You ask, can I do a space or not? There's a word space state right now. And then you can only have a dash or dot after that because you can't have a space after a space. That's the rule of the communication. Okay, cool. Markov sources and approximations to English that we were talking about earlier. On pages 4 and 5, Shannon introduces the key formalism, which sources the Markov processes, also called stochastic processes. Um, a system with finite states, transition probabilities, which is the probability of going from state I to J, and symbol generation, where each transition produces a symbol. Why Markov? Because the next state depends only on the current state, not the entire history, right? Discard what was in the past, just that is currently happening. The genius idea here, which is approximating English, which says that 50% of English is just redundant. Here's where Shannon's paper becomes visceral. Pages 6 to 7 show approximations to English and says that in the zeroth order approximation, all 27 symbols are equally likely and independent. So much entropy. Gibberish, unreadable. First order approximation goes on to say that each symbol chosen independently, but with English letter frequencies. So you must know that E is the most frequently used English letter, which sits around 12%. After that, there's W, which is 2%, and there's more. So the first order approximation is choosing, yeah. And I mean, sorry, W is like one more and its probability is, frequency probability is 2%. Anyways, so in the first order approximation, we still choose randomly, but based on the frequency percentage of these things, right? Still gibberish, but you see some patterns now. Second order approximation, which is a diagram structure. Each letter is chosen based on the previous letter's frequency. Okay, so we are adding more rules here. Starting to look like words. R appears, dreamy appears like dreamy, like dreamy appears like dreamy. Third order approximation, which is a trigram structure. Each letter is based on the previous two letters. So D, die, was based on one letter before ka probability. Try is based on two letters that are preceding it. Okay, so we are just every order we are adding more structure and more rules to it. So adding more finite automaton state structure to it, for a lack of a better word, which is actually the correct word. Um, now it eerily looks like English at this, at this point. Phrases start to emerge. Word level first order, where things make a little more sense, and word level second order, which is a bigram structure where you look at the previous word to predict the next word. Am I getting a hint of transformers and LLMs creating or predicting what the next word should be? Something like that. Am I hinting at that? I am. That's a bigram structure, right? Imagine if you could do a trigram structure. Well, that's what a compiler is. It looks at two things before and then it decides what's supposed to be done later. So you'll do this in 340 and see how, like, these things are just translating everywhere, like here and there, and it's just all connected for some reason. It's just because information theory. Anyways, this is profound, right? Wasn't this like didn't it like create some sort of enlightenment, right? Like some things are connected. Okay, I don't get like everything is connected, but some things did seem connected. This is profound. Sequence of four or more words can easily be placed in sentences without unusual or strained constructions, right? The implication of this is a mathematical process capturing statistical structure can recreate language. That's what we were coming to. Ergodic versus mixed sources. Ergodic versus mixed sources. Ergodic is when there's a source where every sequence has the same statistical properties. What you see is what you get everywhere. Just think of it like that. Mixed is where multiple ergodic sources are blended. Start with one, stick with it forever. Most natural languages are approximately ergodic. This matters because it means that we can treat long sequences as typical. Okay? Yeah. The transition probability matrix. For a first order Markov source on three letters A, B, C, if we are in state A, we go to state B with some probability and then to state C with some probability. Just think of it like that. There's a matrix, and if we are in state A, we are going to state B, we are going to state C with some probabilities, one after the other. Okay, it's dependent on whatever rules you determine, all of that. We'll not go too much into the math anymore. Okay. Let's come to section number 5 of this paper, which is entropy of a source and information rate. The key question that we are asking here is, if we have a source with a known statistical structure, how much information does it produce per symbol? If we have a structure, if we have a source with a known statistical structure, how much information does it produce per symbol? We know the statistical structure of this source. How much information is it going to produce per symbol? We know the source structure and how much information will it produce. We read into source entropy here. If symbols are produced at m symbols per second, then there's another formula where, and you can look at this at page number 17 through 18, where, he goes over an example. We'll not go over it. It's too much math. The fundamental meaning of this is that long sequences of length n from a source with entropy h have probabilities concentrated around 2 to the power minus nh. Just a formula again, okay? If you ever need to use it to calculate something. The interpretation is that a typical long message is equally likely as any other typical message. And there are about 2 to the power hn typical messages of length n. Okay? The implication of this is to specify which of the typical messages was sent, you need h times n number of bits. Per symbol, that's h bits per symbol. This matches the entropy, right? Because it's h. That matches the entropy. Okay, anyways. The redundancy, now we talk about the redundancy versus the entropy here. The relative entropy is h divided by the maximum possible entropy of the same alphabet. another formula. The redundancy is another formula, which you can go over in pages 17 through 18. It's just, just formulas. You can look at it, you can plug in the values that we have been talking about, and you can come to the results. The meaning of this formula is half is determined, half is free for English, right? 50% was redundant, so half is determined and half is free. Shannon gives evidence for it, which is calculation of entropy for an n-gram approximation. Deleting 50% of letters and trying to restore them usually works. This is teleportation. So when they'll be doing that, yes, there'll be like inefficiency on the other end, but most of the message will be registered because 50% of it is just garbage. You can still get rid of. How often do you use the letter Z? How often do you use the letter Q? How often do you use the letter V? Right? You can get rid of them and probably still be able to communicate with me. Right? You'll sound a little funny, but it'll be fine. Okay. um, Section 6.
It's like reading Latin. Yeah. Is the best way to put that.
Yeah, simpler language. Um, and then think of like languages like Sanskrit, which have 52 characters, right? Even at that,
Even like Marathi and Hindi.
yeah, they have like 52 characters, but even then it's so coherent and structurally sound, right?
Yeah.
Which means that the noise in that like language transmission is much, much, much less because it's just engineered to be like that. There's very less loss in that language. You get rid of a few letters, you'll actually have a problem. Okay. The noiseless channel of fundamental I swear I won't do more math after this. Okay, I'll skip over all the math. Okay. uh Let a source have entropy H and a channel have capacity C, then it is possible to encode the output of the source in such a way as to transmit the average rate C by H symbols per second over the channel where epsilon is the arbitrarily where epsilon is arbitrarily small. It is not possible to transmit at an average rate greater than C by H. Consider this a fundamental truth. What
What is that?
uh that is the formula on page number 15. Uh there's descriptions of this formula. I'm just going to skip that. There's also a proof given, which also I'm going to skip because it's more math and anyone can just go over it. Okay. Intuition about why this works is because think of the channel as a bucket that holds C bits per second. The source as water flowing at h bits per symbol. So the bucket can hold C per second. Bucket is the medium, it can hold C per second. The source is the thing where water flows from at h bits per second. We are following here. If you send one symbol per second of h bits, you use h bits of channel capacity because 1 times h. So if you do 1 per second, you're sending h. Capacity is c, right? To send c divided by h things, you need to do it c times. You need c bits, right? Because c times h by c times c by h is 1, right? Cross cross cancel
Yes.
cancel. So if you're sending h, capacity is c and you need to fill it all at once, so like
All of that
one,
goes into C.
yeah, so all of it equals to c, then you have to send c number of h's, and then you'll get there, right? Have like a one cut out everything. The encoding just arranges things so high probability messages so that high probability messages use less space. So that's what the encoding is supposed to do. What the encoding does is it arranges things in a way so that high probability messages, which happen often, use less space. That's it. It's like Huffman coding, which came later and implements Shannon's theorem. Yep. Whew. Noisy channels, equivocation, and mutual information. I think this is the last, I think, fourth last slide. Okay. The real world noise. Up to now, we had an assumption that we are working with perfect transmission, but real channels have noise because it's reality. Think of lightning strikes, thermal noise, interference. Signals get corrupted because of this, right? The most general model is a finite state noisy channel with transition probabilities. So, meaning that if a channel is in the state and the symbol is sent, probability of receiving and going to state what? The problem here is that suppose we send a binary digit, Suppose we send binary digits at 1,000 symbols per second, but 1% of the symbols are corrupted. We get 990 bits per second, right? Because 10 were corrupted, 1% were corrupted. The problem is that it ignores the ambiguity at the receiver. Which error is where?
The corrupted message would still be sent through.
Yeah. So extreme cases that if noise flips every symbol to random 0 or 1, the receiver gets no information at all.
Yeah.
Right? The right measure, equivocation here, is going to be Shannon defines equivocation as a conditional entropy. Remember, we were talking about conditional entropy before. There's a joint probability of sending and receiving, and there is a conditional probability, of I given like, some j. Meaning that on average, what it's trying to calculate is how uncertain are we about what was sent, given what we received is known. Okay, how uncertain are we about what was sent when when we are given what was received by us. Okay, we are just calculating how uncertain about what was sent. Okay, the rate of transmission is the conditional entropy here, which was hx minus hyx. Okay, information sent minus information lost, which is equal to information received. Okay. There's an example of this on page number 20 that you can go over. If we 1% error or error rate on binary symbols, if we receive a 0, the posterior probability, as in the later probability that it was 0, is 99%, but the posterior probability that it was 1 is 1%, because there is a 1% chance that it could have been 1. Per 1,000 symbols, this will translate into 1,000 minus 81, which is 919, right? Bits per second. Theorem number 10, equivocation and error correction. A correction of channel capacity can send enough data to correct all but arbitrarily small fraction of errors. To find errors, the receiver needs information about where and what the errors are. This requires exactly HYX bits per second. There's also a mutual information theory where Shannon shows three equivalent forms of the transmission rate, which is the same formula but shown in another like way. You can take a look at it on page number 20 if you feel like it. These are just formulas that are used to do calculations. I hope that the basic concept of like what entropy is, what conditional entropy is, what probability is here, what a state machine is, the next state depending on the original state, all of that is at least clear. Yeah. Right? Don't have to dwell on the math too much. Cool. Now we move to the noisy channel fundamental theorem. So channel capacity for noisy channels, we already went over this, but sorry, we went over channel capacity, but that was for the perfect world. Definitely, there's also going to be a calculation for noisy channels, right? Like where real world scenario is happening and there's a noisy channel. This is where conditional entropy comes in. Why? Because now there is a condition and we can plug in the value of the conditional entropy and get the actual rates, right? So okay, that is where this is happening. We maximize over all possible input sources, and the intuition is that C is the best transmission rate you can achieve by choosing your input wisely. If we maximize it, then we come to the theoretical best.
Part two now.
Yeah, we are getting into part 2. The main result. Let a discrete channel have capacity C and a discrete source of entropy per second H. If H is smaller than equal to C, remember transmission is H, capacity is C of the medium. If H is smaller than equal to C, then there exists a coding system such that the output of the source can be transmitted over the channel with an arbitrarily small frequency of errors, because you haven't overflown the capacity, or an arbitrarily small equivocation. If H is greater than C though, it is possible to encode the source so that the equivocation is less than h minus c plus epsilon, where epsilon is arbitrarily small. There is no method of encoding which gives an equivocation less than h minus c. Just listen to this and just move on, right? Okay. All it's saying is that, like, if it's less, then it goes through. If it's more, then we can encode it in a way that it's h minus c plus epsilon, and epsilon is arbitrarily small. Very
Is this so that the capacity doesn't get like
yeah, sure. Yeah. And I hope that was, even though that was a very long sentence, it was pretty intuitive. Okay. Because of the things that we have discussed so far.
Yeah.
Anyways, what this means is three cases. If h is smaller than equal to c, then we can achieve error-free transmission. because it hasn't overflown the capacity. So there's literally no possibility of loss. Not perfectly, but arbitrarily close to zero error, right? If H is greater than C, we cannot achieve zero errors, but equivocation is bounded. Like, it's bounded within where it's going to happen. Best equivocation we can achieve is H minus C, which is, fitting it to the capacity, meaning that H minus C bits per second of uncertainty. Fundamental limit is cannot do better than H minus C, though. This is intuitive, right, Sa? And Saket, yes, this is intuitive, right?
Yeah, correct.
A little? Okay, cool. Awesome.
Which part?
Uh, if H is smaller than equal to C, and if H is greater than C, yeah, awesome, cool, perfect. The attainable region. Shannon shows graphically what is possible. Uh, hmm. Shannon shows graphically what is actually possible. The key insight from that, showcase is that to transmit at a rate r, the equivocation must be at least h minus r. We cannot escape this. Just remember this as a truth. Okay. Uh, Moving forward, the conclusion from what we have learned today. Okay. Whew. Information is measurable via entropy. Remember the first formula? H equals to minus summation of pi times log 2 pi.
Yeah.
Very intuitive, huh? Very, this you will not forget. Okay. H equals minus summation of I through n of pi times log pi. Okay. Information is measurable via entropy. Never forget this. I'm sure you'll never forget this. Channels have limits. It has a capacity C that we very clearly defined a lot of times on transmission rate. है ना? There's a noiseless theorem where we can achieve a rate C by H symbols per second with an arbitrarily small error. है ना? There's noisy theorem, which is achieving C bits per second with manageable equivocation of H minus C. Yeah, manageable equivocation. Like if it's greater than C, then we can do H minus C, and that's the theoretical best that we can get to. And then statistics matter. The structure of the source determines what we can send. The philosophical impact of this. Before Shannon, engineers thought that more noise means less throughput. True, but not the whole story. Better channel equals faster transmission, which is also true, but C grows with better channels. Hmm? After Shannon's paper, there's a fundamental limit, C, that depends on the noise structure. We can encode redundantly to combat noise without losing rate, which is the H minus C and H minus R thing that we were talking about. The source's statistics are as important as the channel. So the way the source is created is as important as the medium that we are trying to send things with. As in, if it's a redundant language itself that you're trying to transmit, the thing that you'll transmit will also be redundant unless you bring it down to something that is more sensible. Modern applications of this thing, the crux of why we did all of this is data compression. MP3 uses Shannon's entropy to remove redundancy. Zip files exploit low entropy of human language. So a zip file is created by getting rid of the redundancy in that file. Things that you can remove without destroying the file itself. And then when you reconstruct that file, it probably has those states stored somewhere as another small bit of information, which is the set of instructions on how to get that file back, combines it all together, and then you get your original file back. Zipping it, taking out redundancy, storing what you took out, so the steps to recreate it, and then putting it back together and giving you the file when you request for it. When you compress a PNG file, the quality of it decreases because in the matrices that we are looking at, it takes out features that are redundant, right? It say like every pixel has a color. It'll make sure that it's taken out and every 4 pixel now represents something instead of all 4 of those pixels having colors. That's how you bring the quality of the image down, right? Error correction codes. Hamming codes, turbo codes, LDPC codes all implement Shannon's redundancy idea. Your DNA is error corrected this way. Error correcting codes use Shannon's algorithm. My DNA was inspired by Shannon. Machine learning, cross entropy loss in neural nets. Shannon's entropy formula is used there. Information bottleneck theory connects information theory to deep learning. So its implications can be seen in deep learning and neural nets. LLMs, like we were talking about, next token prediction is literally computing the dependent logarithmic formula that I was talking about. Compression and LLM performance are theoretically linked. That's the Hutter prize. Remember Hutter that I was talking about in the first? Yeah. So if you read this paper carefully enough and reproduce enough stuff, maybe you will figure out a way to win the Hutter prize again, right? Channel coding. 5G achieves rates within 1% of Shannon's limit. Polar codes are approached capacity for many channels. Polar codes approach capacity for many channels.
What is a polar code?
Yeah, so polar code, let me just look it up actually. I don't want to give you an answer. Polar codes and entropy using channels. So polar codes are a class of error correcting codes that achieve the capacity of symmetric binary input discrete memoryless channels by leveraging the phenomena of channel polarization. Let's see, Eli 5. Polar codes are a smart way to send messages over a noisy channel so that message can still be received reliably even when some bits get lost or flipped.
Okay.
Yeah.
Yeah.
So it's another way of transmitting messages, like, carefully.
Yeah.
Why this matters now? In 2025, we are hitting Shannon's limits everywhere. Wireless networks are optimized to nearly theoretical capacity. So we might not have a 7G.
Oh.
Yeah, because
Okay.
6G is being worked on, but
Yeah.
we are nearing our, like, Shannon's capacity right now, which is a theory of all information. But again, we said the same thing for doubling, uh, like, a number of semiconductor in a chip. But look, we are still making steady progress.
Yeah.
Quantum computing will need quantum information theory, which is a similar structure. AI systems learn by compressing data, a deeply Shannon theoretic process. A final thought, Shannon unified communication, information, statistics into one mathematical framework. 76 years later, every technology that transmits data relies on his insights. The paper starts simply, how do we measure information, and ends with a theorem. There exist codes that achieve perfect transmission through noisy channels while staying near the Shannon limit. This wasn't just elegant mathematics. Instead, it was a blueprint for the information age. With that, I'll one last time, remind us like what we are today taking for granted that are all applications of Shannon's, theories. Data compression like MP3 and zip, they exploit redundancy, error correcting codes, uh, machine learning algorithms, large language models which use next token prediction. They literally work on computing conditional entropy. 5G networks, which are working on 1% of Shannon's limit right now, and quantum information, where some framework is extended to quantum systems. Um, every wireless transmission uses channel capacity calculations. Every data center uses compression ratios derived from entropy. Every LLM implicitly minimizes cross entropy loss. And every error correcting code implements Shannon's redundancy principle. The universal limit is that nature pays exactly for extra information. There are no free lunches. This is something that Juan Liu also keeps saying, who's a data mining legend at ASU. I'm taking a class with him this semester, and he runs one of the most prestigious labs at ASU, which is called the Data Mining and Machine Learning Lab. He's one of the speakers that we'll be inviting next semester for a talk.
Oh, okay.
Yeah. Uh, and I'll probably be publishing a paper with one of his PhD students by the end of next semester. Before Shannon, noise reduces capacity proportionally, is what was thought. After Shannon, there exists a precise limit C, and cleverness can approach it. Key insight from this entire thing is that the sources statistics matter as much as the channel. And unifying principle is that information is measurable and limits are fundamental, but they are indeed achievable. And one last closing thought before we take it away is Shannon took a practical engineering problem and found the mathematical beauty. And his 1948 paper unified telegraph, radio, telephone, and computing. 77 years later today, the information age still runs on his theorem, and it will continue to do so as we go into, quantum and even forward. And the legacy that remains is when we stream, when we compress, when we correct errors, or we train AI, we use Shannon.
Mm.
And with that, I'd like to end today's session. Thank you so much for everyone who took the time to join.